So in the last video we talked about quotient sets, but now we want to talk about quotient spaces. Okay, so the idea here we have let X be a topological space. And E is going to be an equivalence relation on X, giving quotient set X mod E, and got this usual projection map pi from X to X mod E with pi X equal pi Y if and only if X E Y. And we declare that a subset, let's call it U bar in X mod E, is open in X mod E if and only if the pre-image pi inverse of U bar is open in X. And so first you want to claim that this is a topology. On X mod E. And well, so firstly, for the empty set contained in X mod E, well, the pre-image of the empty set, that's the set of points which get mapped into the empty set, which is impossible. So this is the empty subset of X, and that means that and of course the empty set is open in X by one of the axioms of topology on X. So the empty set is open in X mod E. And for the full space, well, the pre-image of the full space X mod E is just all of X. And that's open in X. So that means that X mod E is open in X mod E. Now suppose we have a family of open subsets. They're going to be called UI bar. These are subsets of X mod E. Well, then if we look at the pre-image of the union of all these sets UI bar, well, it's one basic fact about how pre-images work. The pre-image of a union is the union of the pre-images. We mentioned this when we first introduced pre-images. And each, remember the UI bar is said to be open with respect to this quotient topology, and by definition that just means that the pre-image pi inverse UI bar is open in X. So that means that pi inverse of the union of the UI bars is a union of open sets. And it's equal to this union here, and each of these sets in the union is open. And that means it's open in X. And so this pre-image is open in X, and by definition of the quotient topology, that means that the union of the UI bars is open in X mod E. And the story with finite intersections is more or less the same. So these are open in X mod E. Okay, so let's just write the argument in a slightly different style. So we define UI to be the preimage of UI bar. So these are all going to be open in X. So the intersection U1 up to UN, that's again open in X. But if we take the preimage of this intersection, that's the same thing as U1 intersect as the intersection of these guys. So that means that this intersection U1 bar, intersection of U1 bar up to UN bar is open in X mod E. Because the definition of being open in X mod E is just that the preimage should be open in X, and preimage is this intersection here, which, as we just said, is open in X. Okay, so that finishes the axioms for topology. We see that this definition of open sets for X mod E does indeed give a topology on X mod E, and we're calling that the quotient topology. So now we need to establish the key property of the quotient topology in terms of continuous maps. Okay, so again we let X be a space, E an equivalence relation. T another space. And F bar a function from X mod E to T. And so that, as we've discussed before, it corresponds to an E-saturated function, which is F bar composed with pi. So that's a function now from X to T instead of from X mod E to T. And then the claim is just that F is continuous if and only if F bar is continuous. Oh, and the proof actually follows. There's a little lemma which you need to state separately. Okay, so let's just do that as a lemma. Pi from X to X mod E is continuous. And this isn't really even a lemma; it's just an observation. In the proof, suppose U bar in X mod E is open. We need to check that pi inverse U bar is open in X. That is just the definition of what it means. To say U bar is open. So in the way the quotient topology is defined just makes it completely tautological that pi is continuous. Okay, so now we can prove the claim. So one way around is now completely clear. So if f bar is continuous, well, this f was defined to be f bar composed with pi, and so that's a composite. So it's a composite of continuous maps, therefore it's continuous. So the other way around is not actually much harder. Suppose f is continuous. Okay, so suppose A is some open subset of T. So we need to check that the f bar inverse of A should be open in X mod E. But what does it mean to say that a set's open in X mod E? Well, by definition, it just means that the preimage pi inverse of it is open in X. But this is just f bar composed with pi inverse of A, which is f inverse of A, right? The preimage. This is the preimage under the composite f bar composed with pi, but f bar composed with pi is just equal to f. So this set that we're looking at here is just f inverse of A, and that holds by continuity of f. Okay, so this completes the proof of this claim here. Continuous maps. So let's actually just rewrite that conclusion. So we can just finish by restating the conclusion there. So we see that there's now a one-to-one correspondence between continuous maps from X mod E to T. They correspond to continuous B saturated maps from X to T. Where a map f bar from X mod E to T just corresponds to the composite f bar composed with pi going from X to T. And so we'll be able to use this to produce a whole bunch of maps out of quotient spaces, and therefore identify various interesting quotient spaces up to homeomorphism. But that'll be in the next video.